Welcome and Happy New Year to everyone. This past year I produced 37 videos, which is partly due to my shoulder surgery from a mountain biking accident. Shoulder rehab has one of the longest rehab times, and even with 1 to 2 hours of rehab exercise per day, I had plenty of time to produce videos and come up with topics, which helped me from going crazy. Or let's just say maybe crazier. But nevertheless, let's get on with the topic. Vector network analyzers are the typical go-to piece of equipment when wanting to measure RF impedances. But not everyone has a VNA, and sometimes a VNA is not up to the task. Trying to measure the impedance at an elevated voltage or in the presence of large RF signals requires other techniques. Old devices such as the general radio impedance bridge are really not any better than a VNA. Besides, most people don't have one. So let's look at what we can do to make measurements of RF impedance without a VNA, and let SimSmith help us with the mathematics. Let's start with a blank SimSmith circuit. I've got a frequency range from 1 to 30 megahertz, and I'll enable sweep. This really isn't too important. And I'm going to start with the load impedance. And let's make this load impedance, say, be 80 minus J, say 40. And we're going to drive it with, it really doesn't matter what we drive it with, but I'm going to drive with an absolute voltage source of 1 volt. There's no magic to any of this. I'm trying to use different features than I sometimes use just to show that they're available. This absolute voltage of 1 volt here shows 1 volt right there in the load. And it doesn't matter if I change the impedance here in the load, it still shows 1 volt the whole time as I change the impedance. So we're driving it with a 1 volt 0 ohm source. It really doesn't matter. But let's look at how we could measure this impedance out here. Let's pretend this impedance is unknown. Well, there's a lot of things we can do. And we have to do some calculations, but they're very simple. The easiest one we can do is we can say, let's define a variable for impedance from SimSmith, and let's say it's calculated, and it's to me the first calculated one we want to calculate. We can just say L.Z. Hopefully everybody's familiar with that. If I do that, I get this variable Z, SimSmith calculated, the first one, and it matches the load impedance, exactly what you'd expect. Now we can do this a little bit differently. Let's break that down to something a little bit further, and that really is equal to the voltage across, at this point right here, it's the voltage across this point divided by the current going into this point. So SimSmith will give us that answer too. We can say L.V, capital V is the voltage across this point, small v is the voltage across this component, so it really doesn't matter if this is capital V or small v, divided by, we want the current. So L dot, the current going into the component, what doesn't matter again if this is I or small I. Let's make it capital I for the moment. And we'll see that this gives us another variable of the same answer. Again, this could be small v in this case, doesn't change anything. It could be small I, doesn't change anything. They're all the same. But the voltage divided by the current, where you have to take into account phase. And this is one of the things SimSmith is good at. SimSmith, all the variables in SimSmith are complex numbers. The fact that the voltage and current are not in phase at this point in time really doesn't matter. SimSmith takes care of that all for us. And that's a huge, huge advantage. And it helps you understand what's going on. So you're probably saying at this point in time, this is pretty simple stuff. And you're absolutely correct. This is pretty simple stuff. But let's build up on this. I think a lot of people along the way sometimes like it if I go slower. Some people like it if I go faster. You know, it's kind of a hard thing to know which one to do at the moment. So let's now look at this, put a RUSE block in here. With a RUSE block in here, let's build a circuit that's extremely simple. Just a resistor, it's all it has. And what I'm going to do with this resistor, I'm going to give it I'm not going to give it a value, so it's going to force us to give it a value up here. Let's say call it 10 ohms for the moment. If we take this circuit right here and we put a label, so right there, give it a name other than ground, which is a short circuit. Call it V1. If we take and calculate Again, let's give it another one of these variables like we did before. Zsc. Zsc. We'll call this, say, 3. It's the third one we've done. And it's going to equal to V1 divided by R1 dot I, small I. That's the current through this resistor. Now the current, the dot is such that if this voltage is positive and there's a positive current going through here, that the two are correct. So that should give us the right answer. And what we see up here is 80 minus J40 for Zssc3. We can do that a little bit differently. It's hard to measure a current through a resistor. What do we do about that? Well, we come up with another, call it V2, and now the current, instead of being R1 underscore I, what we're going to make that be is parentheses V2 minus V1 parentheses divided by R1 underscore, which is the value, and I need a couple more parentheses here. So this thing right here is the voltage across the resistor. This is the resistance value, voltage divided by the not the resistance value, it's an impedance value. This could be R1, could be, it wouldn't have mattered. R1 could have been 10 plus J5, it wouldn't have mattered. Voltage across this component divided by the impedance of this component is the current, and then we're going to use the voltage going into our device under test, which is still left here. So if we think about this for a minute, we wouldn't put complex number in there. We put just a resistor in here. We could use an oscilloscope to make these two measurements. If we made a measurement of V1 and we made a measurement of V2 with our oscilloscope, and we were careful how we did this, and then so that we could subtract V1 and V2 and use V1 in our calculation, we could calculate the impedance. Now, you may not like doing this because V1 and V2 may be large voltages. Say there may be a couple volts, but yet the voltage across this resistor could be small. You could make the resistor larger, but if you don't know what this impedance is out here, this circuit kind of is problematic in that you're taking the difference between two different channels on the scope. And let's just look and see if we can come up with a slightly better circuit than this. Well, the next circuit I would come up with would be, if I don't want to use calculated voltages across my scope, I just want to use individual voltages. I use one channel to measure voltage, one channel to measure current. So let's do that. Let's break that resistor there, break that, move this down here. Now, the scope has one connection to ground all the time. What this does is this lets me use one channel to measure the voltage, one channel to measure the current. And this will work just fine. However, what we've done here is we've just shorted out this resistor. We really need to remove this ground right there. And if we do that, this circuit will work correctly too. Now, the voltage is V1. The current is V2 over R1, not V2 minus V1, which is good. And we wanted that. That was the thing we were trying to get rid of. We don't need the extra parentheses now. But unfortunately, the polarity here is wrong. When the voltage is positive to minus here, the current will flow this way, so this voltage is negative. So we really want that to be minus V2. Now if we do that, we get the same answer again. Everything's working just perfectly. And this circuit would be a good circuit to use if it wasn't for the fact that most of our generators have a connection to ground. When I say generator, it can be a transmitter. It could be an amateur radio transmitter you've opened up and use it as a signal generator. I've done that on most of my transmitters. And it could be a signal generator. It could be anything else. But if it's not a battery-powered oscillator or something like that, you have a problem with one of these connections generally being ground. And so let's look for a better circuit. So now I've just cleaned up the previous RUSE block and brought it back to where you would normally start with just the two labels, P1, P2, which are the endpoints and a wire connecting them together. I didn't previously name this. Let's name this. Let's give this a name, say like Z measure. It's nice to label the names of the RUSE blocks. It'll show up here to the extent that SimSmith will allow you to fit whatever's in here. It'll make it small enough. Sometimes it's too small to read. So be careful you can't put a sentence in here. And the first thing let's do, let's come up with another circuit. What I'm going to do is make a circuit that's like a bridge circuit. So let's take, here's the device under test from here to ground. And that's good because you might want this might want to be a piece of coax that goes out to an antenna. And if it's just a component, it doesn't matter if it's connected to ground or not. Let's put a resistor, bring the resistor in, hit the R button when I'm centered on here and it rotates it. And let's make that a little bit bigger. Put that down some. And put an impedance in series with the device, the impedance that we're trying to measure. Let's also now copy this resistor. Grab it, Control C, Control V. Bring another resistor in here and a third one. Let's put these resistors in series. And connect them to ground. And connect everything together like this. Now let's have two labels, V1 and V2 like before. Grab the label, or just point over it, the R button, whoops, the R key, rotate it. Control C on that, Control V. I didn't need it named R. Change this one to be V2. This is a little tricky to type, talk, and do everything at the same time. Okay. Grab it, bring it over here. And there's the circuit. Now we're going to do a couple things. What if I make this, say, be 50 ohms? And I make this be 50 ohms. And I make this be 50 ohms. Now there's no magic to these resistor values. But what is interesting about doing it this way is a couple things. If I have a transmitter here that maybe it's a little QRP transmitter I'm using as my generator, maybe it's something else, it'd be nice to face this generator with some tolerable impedance. When I say tolerable, I mean not really. SWR say less than 2 or 3 to 1. And this circuit right here, no matter what this impedance is, if this impedance is incredibly high, this resistor doesn't matter anymore, and the generator sees 50 plus 50 or 100 ohms or 2 to 1 SWR. If this is dead short, it sees 100 in parallel with 50, which is 33. It actually sees worse SWR up here, so you could make these resistors even lower, make them say be 40. You could make it symmetrical. So, but in the way it's shown right now, the SWR will always be less than 2 to 1, which is not really bad for most transmitters. 50 ohm resistors are easy to come by. And I built a circuit up like this with some 1206 49.9 ohm resistors. These were I had measured these to be the same. Didn't matter what value they were the same. And this one just happened to be the same too. And there's the circuit. So let's look at what we can do to understand what's going on here. So what we're going to do is we're going to make a voltage divider here. We know that this voltage here from circuit theory, start with this voltage up here times this impedance divided by the sum of these two impedances equals this voltage. And of course you have to keep account of phase and everything. But SimSmith can do this for us very easily. There's a reason for using this voltage tapped down, and that's because I can use two channels of the scope on the same range. compare the ranges to be equal. It's nice to have these voltages be similar. And we just multiply this voltage times 2 to go up to here. You can do it lots of different ways. And however I do it, there's, someone else may have a better idea, and that's perfectly fine. But let's look at some stuff right now. The first thing let's do is look at the actual waveforms. So we type the command wave, and let's name it. And we're going to call it V1 peak. And by the way, we can do this with peak voltages or RMS voltages. When you do the division, the units go away, whether they're peak or RMS. V1 peak, and what we're going to look at is we're going to look at V1, and that's V1 relative to ground. If there is no ground in this circuit, it's relative to the bottom terminal of P2. But we have ground here, so it's V1 to ground. And then what we're going to do is we're going to put it on the Y1 axis, and we're going to label the Y1 axis as V for volts. Now, we don't need to say Y1 here. We get that for free, but we can say Y1 if we want to. It doesn't matter. And let's bring up the square chart, and there's our signal. Now, what we have here is 2 cycles of it. That's the way SimSmith always does this. It gives us 2 cycles of this waveform, and this waveform does not start at 0 phase, because the 0 phase is determined by the generator. And this is in series, this voltage here is the division ratio between these 2 impedances, and this one happens to be reactive. So we can do the same thing now for V2. If you understand this stuff, this is probably like watching grass grow. If you don't understand it, maybe it's useful. Just bear with me for a moment here. We'll look at V2 peak. We do not need to label the axis. That's V2 we're going to look at now. We do not need to label the axis again. Matter of fact, if we do and label something different, SimSmith won't like that. We don't need to say it's Y1 either. Y1 is the default axis. I'm just doing these things a couple different ways. Now we see voltage 1 and voltage 2. Voltage 2 is 50% of what the generator produced. The generator produced a volt RMS, which is 1.4 volts peak, and we see V2 being 0.707 volts peak. Everything looks good. Now let's continue on. And by the way, if we want to make these measurements a little bit more accurately than us doing something like me dragging this around here and trying to find the peak, there's a command in SimSmith called peak. And this, let's just do peak V1. Again, it'll go on axis Y1. And peak V2. And it again goes on axis Y1. And we have a line that's drawn that's asymptotic to the top of those 2 traces. And if we were concerned about making the measurement at 10 megahertz, we would look at this point, 10 megahertz. So we could see it. And now notice I can't quite get on 10 megahertz here, and that's because I went from 5 to 20. Let's see. You have to get enough points in here to make it fit, or you can do. There's lots of different things we can do here, but I'll just increase the number of points for right now. We can get very close to the right frequency, and we see that the V1 is 0.9299 volts peak, and V2 is 0.707 volts peak. Now, let's also look at the difference. When we make these measurements on a scope, I'm using this screen as a scope. These 2 lines at the top could be the markers on your scope that you've set to read the voltages. And we need to measure the phase difference between the 2 of these. Now, SimSmith deals in phase difference in degrees, but your scope does not measure degrees. Maybe some new scopes measure degrees, but most scopes measure the difference in time. So we can take care of that easily enough. Let's plot. See if I can get this right. Let's come up with a variable called, say, delay V1 to V2. So that's going to be the label we're going to use. And what we're going to plot is going to be kind of an ugly thing, but let's start off with, it's the, put it in parentheses because I have to do some calculations here. It's the angle of V1, And SimSmith keeps track of that. Minus the angle of V2. That's the difference. That's the difference in angles in degrees. Now we need to convert degrees to something like nanoseconds or something else. So we divide that by, oh man, I hope I get this right. Divided by, better put this in parentheses, divided by 360, because there's 360 degrees in a full cycle, times the frequency we want to deal with, G dot megahertz. These are both in the denominator still. I'm struggling here. 1 E. This is going to be 10 to the 6th, 10 to the minus 3 I need to compensate for to give me nanoseconds directly. I think that's it. Comma. We'll label our axis, our Y2 axis, say nanoseconds. And we need to tell it now we're going to put it on Y2 for sure. I think that's good enough. Let's see what happens here. Okay. So what we have is we have a curve here now. And the curve is because as we sweep in frequency, even though the phase angles for a given frequency independent load, as we change frequency, the phase difference between these two signals will change in time, but it will not change in degrees. And that's probably worth plotting too. I mean, you can use SimSmith to do some very cool things here. If we take this and just copy it, Control C, put it down here, Control V, and let's delay V1 to V2. Let's just call it, say, degrees. V1 to V2, and all we're going to plot is angle 1 minus angle 2. And we're going to put it on Y2 also. We see that it's a constant 9.46 degrees over the frequency. But this gives it to you in nanoseconds. And nanoseconds is what we really want. So let's get rid of this. Just get rid of this plot. We don't need that anymore. If you have a scope that is capable of giving you the difference in degrees, you didn't need to plot it this way. You could have just plotted the angle. Now, these calculations here are for SimSmith's use, not for you to use at all. What you're going to do is something completely different. You're going to measure these voltages on a scope, and then we're going to use SimSmith to back calculate what this impedance is. So let's do that. We're going to measure 3 things on our scope, and we're going to label them as variables. First one's going to be V1 measure, and I'm going to put these up on the top. And the reason I'm putting them at the top without doing anything with them is to force SimSmith to give me some parameter blocks here that I can fill in later, and I want them in order. So the first thing we're going to do is V1 measure, V2 measure, and then the last thing we're going to do is something called V1 to, can't put spaces in these labels, to V2. You have to put underscores or something if you want a space. Okay, I created 3 variables here now. Now notice what SimSmith did. It put numbers in here, and these numbers happen to be the right values. And the reason they're the right values are because I had put these numbers in previously before I deleted everything to try to have a chance of doing this accurately. If I had done this out of the blue without having done a practice, I'm doing it on the fly, but if I had done it without practicing, it would not have worked the first time. Trust me. I mean, I'm pretty good at this, but there's no way in the world I'm good enough to get this to be right 100% the first time. So these would be the values you would read off your scope and you'd put them in. You'd put them into your circuit. Now, what will we do to make SimSmith calculate this circuit for us? And the first thing we do is let's declare a variable that we're going to use internally. And this is just for some housekeeping. We're going to call it delay. And that's going to be equal to, now delay will not show up here because it's a local variable, so we won't see it. And we're going to set delay to be V1 to V2 times G.MHz, so that's 10 megahertz, so that's 10 megahertz times 1 E6 to get it back to hertz, which we need it in hertz, times 2 times pi. We need that to get that's delay in radians. Now the next thing we're going to do is we need to get V1 into a form where it's a complex number. We measured two scalar numbers with our scope, but we need to get V1 to be a complex number to be able to do the math right, because its phase difference is different than V2. So we'll make it a private or public, a non-public variable too. Let's call it V1, say calculated. We're going to calculate that. And that will give us the same number that SimSmith has in here, but we don't have it because we just measured it with a scope. So V1 calc equals, and this is a pretty easy calculation. This is the way you convert to complex numbers all the time. So it's V1 measured, it's the measured value of V1 times the cosine of the phase delay in radians plus J times V1 measured times sine of the delay, of the difference of the phase delay in radians. And if we do that, we have a complex number for V1 and V2. We have a complex number for V1, and V2 is a scalar number because we calculated the phase difference between the two. We don't need to know the phase of each one of these. In this case, the phase of this one would be 0 because there's no phase difference between this generator and here. If we had a generator that had impedance in the output, then both of these would have been complex numbers in SimSmith. But when you measure it with a scope, you can call either one of them phase of 0, and the other one is, the only thing you have to worry about is the difference in phase. So for the last step we're going to do is we're going to do Zcalc. We're going to calculate now what our measured values are going to give us for an answer. And this is the piece that we're using SimSmith to help you with the calculation. If you were to do this by hand, the likelihood of most people, myself included, getting it right the first time is probably pretty low unless I'm really, really, really careful. So what we're going to do is we're going to do R1 underscore, which is the value of this top resistor, times the number we just calculated, divided by parentheses 2 times the measured value for V2 minus V1 calculated. And that should be it. Let's see what we get for an answer. I need to put numbers in here yet. Now, in the case when I did this before, when I made these measurements, I made measurements for, I did not have an 80 minus J40 load. I had an 80 ohm load, and I think this was I think it's 300 390 picofarads or something like that. Anyways, it gave me this value roughly at 10 megahertz. I measured something like 0.92 volts here on my scope. I measured 0.71 volts on my scope here, which is pretty accurate. And I measured a phase delay of 2. Geez, what was that? 2.6 nanoseconds. Now, we need to know if this is positive or negative. There's one little thing I didn't mention here, and let's put a little comment in here. If we want to know so the value of the delay is going to be positive if V1 leads V2. So pink trace got the 0 before the blue trace did, so that means we need to have a negative 2.6 nanoseconds here. And that gives us a calculated number of 77.71 minus J37.3, which is actually pretty close to 80 minus J40. And this is done with a scope, not a terribly expensive scope. And it's all by putting these 3 lines of code right here in SimSmith. You can get SimSmith to do the math for you. So, pause the video, write these down if you want, copy them or whatever. There's one more thing we can do here if we wanted to, and that's we could do a Smith chart. We could plot on the Smith chart Zcalc, and that'll show us how close the 2 points are. So we go here, and the red dot is L. L is the 80 minus J40, right there, 80 minus J40. I didn't quite get on it perfectly, but it's 80 minus J40. And then this is a trace. And this impedance will change with frequency because we would not get these same numbers with different frequencies. Even if this load was constant with frequency, these would be varying. But these were valid at 10 megahertz, so 10 megahertz where the circle is, that's what's valid. So right there, that point. Now let's look at this on a big scale things. Is this close enough of an impedance to measure it to be happy? If it is, this is a very reasonable way of doing things. I didn't exercise a huge amount of caution when I built this. I built these with some 1/4 watt resistors on a little solid piece of copper plane. And they were all 49.99 ohm 1/4 watt resistors. I did not use the little clips, the ground clips on the scope. I had a little piece of wire sticking up that was like a cradle that touched the ground part of the scope, and then the probe was right there. And I made the 2 measurements. I held them there. I captured this waveform on the scope and then stopped the refresh. So it's nice to have a scope that you can do a single trace and then stop in terms of holding stuff, but you don't get any more accuracy. If you're careful enough and hold it there with a regular conventional scope that has no storage, you can make the same measurements just as accurately as this. These numbers are pretty close together. If we look at this, let's look at these again closely. This one represents a gamma of 0.368 at minus 36 degrees, and this is 0.349 at minus 37 degrees. There's hardly any circuit you would measure that you would do a whole lot different between those 2 numbers. It might change a matching network you'd build by a few picofarads or something, but this will get you awfully close. And this means that if we were to take this network and make these 10 watt resistors, say, and make this some say 10 watt resistor too, we could put 20 or 30 watts into this circuit easily and have a very large voltage that we're capable of overriding any outside RF interference. And that's the kind of stuff you need to do sometimes at 160 meters where you have a lot of broadcast interference. A lot of little VNAs use a broadband power detector inside, and some use a receiver. The ones that you have a double DDS synthesizer in them, a lot of times will offset the receive frequency coming back to be 5 kilohertz or 10 kilohertz away from the signal that went out. That gives you some improvement in terms of being able to make a measurement in the presence of strong, slightly out of band signals. But nevertheless, you get to a point where you can't make the measurement anymore, and the only thing you can possibly do at that point in time is up the power. Now, not all VNAs are created equal. My 4170 puts out a nominal minus 18 dBm into a 50 ohm load, which is pretty low. A lot of the other VNAs put a little bit more power out, but even the highest power ones I've ever seen put out about plus 10 dBm. And plus 10 dBm is nowhere near to a watt. A watt's plus 30, so that's 20 dB more. So if you were able to put a watt into this circuit, you would be able to withstand 20 dB stronger signals, out of band signals here, that would have an effect on your measurements. This is not the only circuit you can use. You can put a directional coupler in here. I've used directional couplers before. They get voltage outputs. You measure the voltage outputs and you measure the phase. And based on the coupling coefficient, you change the gain here. But this is a pretty simple thing to do. And all I did here to get this formula was to change the order of calculation, and that's shown up here. And this is a fairly simple thing to do. The hard part is for you to maintain your concentration long enough to do all these complex number calculations and not make a mistake. Anyways, this is a simple video that's easy to do. The calculations are more difficult, to say the least, but that's often the way things work, and that's why we have a computer to do the work for us. Hopefully you've enjoyed this video. If you do, let me know. If this has been too long and drawn out and too boring, let me know about that. If you like videos that are more long and drawn out like this one, let me know also. Thank you very much.